Now we start to look in earnest at Alberta Science 9, Topic B3, the origins of the periodic table as part of the chemical nature of matter. The specific learning outcome we are focused on is that students will demonstrate understanding of the origins of the periodic table and relate patterns in the physical and chemical properties of elements to their positions in the periodic table, focusing on the first 11 elements. Introduction. The periodic table is one of the most important tools in chemistry. It helps scientists organize and understand the elements, which are the basic building blocks of all matter. To fully appreciate the periodic table, it is helpful to know how it was developed and how it reveals patterns in the properties of elements, especially the first 18 elements. Origins of the periodic table. The idea of organizing elements began in the early 19th century when scientists noticed that certain elements had similar properties. Dmitry Mendeleev, a Russian chemist, is credited with creating the first widely recognized version of the periodic table in 1869. Mendeleev arranged the elements by increasing atomic mass and grouped them so that elements with similar properties were in the same columns. He even left gaps for elements that had not yet been discovered, predicting their properties based on the patterns he observed. Later, scientists realized that the atomic number, which is the number of protons in an atom's nucleus, was a better way to organize the elements. This led to the modern periodic table, where elements are arranged in order of increasing atomic number. The periodic table is structured in rows, called periods, and columns, called groups or families. This current structure was actually developed by Paul Dirac, following the work of Wolfgang Pauli. Patterns in the periodic table. The periodic table is not just a list. It shows patterns in the physical and chemical properties of elements. These patterns are called periodic trends. The first 18 elements, which make up the first 3 periods, are a great example of these trends. Our first 18 elements are hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Physical properties. The physical properties includes things like state, solid, liquid, or gas, color, and melting point. For example, hydrogen and helium are gases at room temperature, while lithium, beryllium, and boron are solids. As you move across a period from left to right, elements tend to change from metals to nonmetals. For instance, in period 2, lithium and beryllium are metals, boron is a metalloid, and carbon, nitrogen, oxygen, and fluorine are nonmetals. Chemical properties. Chemical properties describe how elements react with other substances. Elements in the same group often have similar chemical properties because they have the same number of electrons in their outer shell. For example, group 1 contains lithium and sodium, which are both highly reactive metals. Group 17 contains fluorine and chlorine, which are both reactive nonmetals known as halogens. The noble gases, like helium, neon, and argon, group 18, are very unreactive. This is because their outer electron shells are full, making them stable. So, electron configuration and patterns. The arrangement of electrons in an atom is called its electron configuration. The periodic table is organized so that elements with similar electron configurations are in the same group. For example, all group 1 elements have 1 electron in their outer shell, making them react in similar ways. As you move across a period, the number of electrons in the outer shell increases. This affects how the elements bond with others. For example, oxygen has 6 electrons in its outer shell and needs 2 more to be full, so it often forms bonds with 2 hydrogen atoms to make water. So the periodic trends. Some important periodic trends include atomic radius. The size of an atom decreases across a period, from left to right, and increases down a group, from top to bottom. Ionization energy. The energy needed to remove an electron increases across a period and decreases down a group. Electronegativity. The ability of an atom to attract electrons increases across a period and decreases down a group. These trends help explain why elements behave the way they do. The one of these that is most counterintuitive is probably the atomic radius. As we go from left to right, we add more protons and neutrons to the nucleus, so you would think that would make the atom bigger. It makes the nucleus bigger, but the nucleus is tiny compared to the electron orbits. And when you don't have many electrons in that orbit, they tend to have a very large and eccentric orbit, almost as if they are reaching out for neighboring atoms to react with and form those bonds with. So the size of an atom is determined largely by the reach of its electrons and their orbits. And that's what increases when you have just a small number of electrons in a shell or a collection of allowed electron orbits. So in conclusion, the periodic table is more than just a chart. It is a powerful tool that shows the relationships between elements. Its origins go back to scientists like Mendeleev, who noticed patterns in the properties of elements. By focusing on the first 18 elements, we could see how the periodic table organizes elements by their atomic number and reveals patterns in their physical and chemical properties. Understanding these patterns helps us predict how elements will behave and how they can be used in science and everyday life. Let's check for understanding. Who is credited with creating the first widely recognized periodic table? Marie Curie, Albert Einstein, Dmitri Mendeleev, or Isaac Newton? Pause now if you need more time. Dmitri Mendeleev is widely recognized for making the first periodic table. What is the primary factor that determines the order of elements in the modern periodic table? Atomic mass, atomic number, density, or melting point? Pause now if you need more time. It is the atomic number, the number of protons in the nucleus, which matches the number of electrons in the orbital shells. Which of the following elements is a noble gas? You may want to refer to a periodic table for this one. Is it hydrogen, neon, nitrogen, or oxygen? Pause now if you need more time, even just to search for that periodic table online. There are many. Neon is the noble gas. Those noble gases are group 18 at the far right-hand side of the table. Which element in the first 18 elements has the highest electronegativity? Remember the rules we had for where electronegativity increases between left and right and up and down. And look at the positions of the elements on the periodic table. Is it carbon, chlorine, fluorine, or sodium? Pause now if you need more time. It's fluorine. So electronegativity increases as you go to the right and as you go up. How do the chemical properties of elements change as you move across a period from left to right in the periodic table? They become less metallic, more reactive with water, or they remain the same. Pause now if you need more time. they become less metallic. The far left are all metals, and then we move into the metalloids before we get to the nonmetals, and finally the noble gases. If you have any questions or feedback, please leave them in the comments. I will try to respond quickly, or at least in a timely fashion. If you have any suggestions for how to improve the slides, I am very open to those suggestions and I can make the updates accordingly.